Problems involving friction. Example 1. A 20 kilogram block sits on a rough surface. The coefficient of friction is given, 0.7. 120 Newton force is applied in this direction by this person, and we need to calculate acceleration. Let's start by calculating the value of R, the normal reaction. Taking this direction as positive, there's only these two forces to consider. So the resultant force would be 0. There's no acceleration vertically, so if this is the positive direction, then R minus W is equal to 0. Yeah, the resultant force is 0. So R is equal to W. W there is the weight of the block, so it's 20 times G. So R is equal to 196 newtons. And now we use the value of R to calculate the maximum value that friction can take. So 0.6 times R gives us 137.2 newtons. That's the maximum value that you could have on this side. So friction varies between 0 and 137.2 newtons. If the force applied in this direction is 120 newtons, then the frictional force, which lies in between these two values, will also be 120 newtons in the opposing direction, like so. Now using F equals ma, we can work out acceleration if there is any. So the resultant force horizontally is 0. So the acceleration is 0. This force applied was not sufficient to overcome friction, so the block doesn't move. Part B. So this time the person tries even harder and applies a force of 200 newtons. We still have the same values from before for the coefficient of friction, the mass of the block, the weight of the block, and so on. So the force of friction will be any value between 0 and its maximum, 137.2 newtons. So we can see already that this force, this horizontal force, is sufficient to overcome the maximum frictional force. So friction is 137.2. So if we take this direction as positive, F equals ma, the resultant force will be 200 minus 137.2 equals the mass times the acceleration, and we can solve to work out acceleration and the direction of acceleration. So 3.14 meters per second squared. Part C. This time the person applies a 200 Newton force, which is at an angle of 30 degrees above the horizontal. The coefficient of friction is still the same, but this force will have a vertical component and a horizontal component. So R will now change. It's not the same as before. Our two components, and this is our right angle triangle, resolving forces vertically. So this direction is taken as positive. So we have R plus 200 sine 30 minus 20G is equal to 0. The resultant force vertically is 0. There is no acceleration vertically, nothing going on in the vertical direction. So solving to work out R is equal to 96 newtons. And now using F equals mu R, we can work out the maximum frictional force that's possible. So multiplying, that gives us a friction value between 0 and 67.2 newtons. So looking at horizontal forces, we need to work out the value of F. What's the frictional force here? It all depends on the horizontal component here of this force. These are the only two horizontal forces. So 200 cos 30 gives us 173.2 newtons. This force is sufficient to overcome the maximum frictional force. So F will be 67.2 newtons, the maximum possible frictional force. Okay, so here's the maximum frictional force, and if we take this direction as positive and look at horizontal forces, so we have 200 cos 30 minus 67.2 equals the mass times acceleration. So the resultant force here on the left hand side, which is 106 newtons, mass of 20 kilograms, and then the acceleration is 5.30 meters per second squared. It's a positive value, so it's in the same direction as this arrow here. Now if you want, you can simplify your sketch, because this 200 Newton force, once you've resolved it into its horizontal and vertical component, you no longer really need this on your diagram, because you've replaced it with these two components which are perpendicular to each other. So you can think of it like this, and these values can be simplified like so. So I can remove that 200 Newton force completely from the diagram, and all I've done here is I'm going to take this 100 Newton force, it's vertically upwards and it's applied to that block, so I'm going to move it from there to here like so. And this diagram looks greatly simplified compared to what we had before, which was this. So you can either work with this diagram, or you can simplify and work with this. It's very easy to see all of the horizontal and vertical forces in this diagram compared to this one.